Here's another example that'll let us see the variation of parameters process. We have the non-homogeneous system x prime equals the 2 by 2 matrix 2, negative 1, 4, 2 times x plus the column vector sine 2t, 2 cosine 2t times e to the 2t. I'd like you to go ahead and find lambda, find k, and then form the complementary solution. Solving the determinant 2 minus lambda, negative 1, 4, 2 minus lambda equals 0 gives us that lambda equals 2 plus or minus 2i. I've said before I only use the plus complex eigenvalue to find our eigenvector, and so we have the system with the 2 by 2 matrix negative 2i, negative 1, 4, and negative 2i times k equals 0. And these rows represent equivalent equations. I've chosen the top row, and I have negative 2i k1 equals k2. At this point, we actually have a choice. I chose to let k1 equal 1, giving me k2 equals negative 2i, so that the vector k is equal to the column vector 1, negative 2i, giving us 1, 0 for b1 and 0, negative 2 for b2. And then our complementary solution is e to the 2t from the real part of the eigenvalue times c1, 1, 0 cosine 2t minus 0, negative 2 sine 2t plus e to the 2t c2, 0, negative 2 cosine 2t plus 1, 0 sine 2t. I referred to a choice up here with the negative 2i k1 equals k2. If you had chosen to let k1 equal I, then you'd have that k2 is equal to 2. And your k would then equal 0, 2 plus 1, 0, I, which looks different. It'll give us a different fundamental matrix. But at the end of the entire process, the answer that you get will be the same as the answer that I'm about to get. Speaking of the fundamental matrix, let's turn this complementary solution into a form that includes the fundamental matrix. So we're going to write it as x sub c is equal to phi times c. In that form, we've got e to the 2t as a factor in every entry, and all of the sines and cosines have as their arguments 2t. That in mind, reading across, we have the cosine and the sine, and then the bottom row is the sine and the negative cosine, that matrix times c. So now we have phi. We then need to find phi inverse, and for that, we need the determinant of phi. The determinant of phi is the reason that I wrote the e to the 2t inside of the matrix rather than multiplying it by e to the 2t, because it doesn't work exactly how you might expect if you haven't worked with determinants and scalars before. Multiplying e to the 2t cosine 2t by negative 2 e to the 2t cosine 2t. I mean, we're going to get a cosine squared in there. There's a negative because, we're multiplying a positive by a negative, but then we subtract lower left times upper right, and we're going to get a sine squared. At the end of all of this, what we end up with is that the determinant is negative 1 over 2e to the 4t. That gives us a phi inverse that has that negative 1 over 2e to the 4t. And then we switch places of the entries in the upper left and lower right. And we change the signs on the entries in the upper right and lower left. You'll notice that we can divide e to the 4t into e to the 2t in every case. The minus 1/2 out front is going to multiply all of the terms. And the result is that phi inverse is equal to e to the negative 2t. I'm leaving that out in front of the whole matrix because it's just going to be easier to work with here. Times the cosine of 2t, 1/2 sine of 2t, sine of 2t, and negative cosine of 2t. Negative 1/2 cosine of 2t. The reason we need phi inverse is because we need the integral of phi inverse times f with respect to t. Well, as it turns out, Phi inverse has that factor of e to the negative 2t. F was that column vector, remember, sine 2t, 2 cosine 2t, times e to the 2t. The e to the 2t and the e to the negative 2t, they divide out. We don't have to worry about those. Multiplying the matrix by the vector is going to give us cosine times sine plus sine times cosine, and all the arguments are 2t. That is 2 times the sine of 2t times the cosine of 2t. Moving to the bottom row, sine times sine minus cosine times cosine, because the 1/2 and the 2 multiply to 1. That's sine squared of 2t minus the cosine squared of 2t. And before we go any further to integrate with respect to t, we can recognize that these are formulas from trig, right? 2 sine theta cosine theta is the sine of 2 theta. So that top entry becomes sine of 4t. Sine squared minus cosine squared of theta would be negative cosine 2 theta. So here it's negative cosine 4t. Integrating that with respect to t is going to give us negative 1/4 cosine of 4t and negative 1/4 sine of 4t. From our formula, remember that the fate of this is to be multiplied by phi. So I'm going to write phi with the factor of e to the 2t outside, and then the rest is basically the fundamental matrix. Cosine, sine, 2 cosine, nope, 2 sine, and then negative cosine, all of 2t, times what we got from our integrating, negative 1/4 cosine of 4t, negative 1/4 sine of 4t. This also is going to use a little bit of trig to clean up. We're going to multiply the cosine of 2t by the cosine of 4t. Yeah, there's a negative 1/4 there. And then sine of 2t times negative 1/4 sine of 4t. What we end up with is negative 1/4 times the cosine of 2t cosine of 4t. I'll factor out the 1/4, so it's plus the sine of 2t sine of 4t, which you may or may not recognize, but it's actually the difference formula for the cosine function. We'll get back to that. 2 sine 2t times negative 1/4 cosine 4t, and then negative cosine 2t times negative 1/4 sine 4t is going to give us a 1/2 negative sine 2t cosine 4t plus cosine 2t sine 4t. That's also an identity. We're going to end up here with e to the 2t times negative 1/4 cosine of 2t and 1/2 sine of 2t. The top row is like the cosine of alpha minus beta, and the bottom entry is the sine of alpha minus beta. Putting it together with our complementary solution, we get ultimately that x of t is c1 times the column vector cosine 2t 2 sine 2t e to the 2t plus c2 times the column vector sine of 2t negative 2 cosine 2t times e to the 2t plus our xp, which is negative 1/4 cosine 2t 1/2 sine 2t e to the 2t. Now I did this a different way, using that choice that I was talking about, where k2 was equal to 2 and k1 was equal to I. And what I found was that the way I did it, this c2 vector here, the sine 2t and the negative 2 cosine 2t, they had opposite signs. And that's totally fine because it gets rolled into the constant c2. once we get initial conditions, it will all come out in the wash. So if your answer is off by a constant, but you still have the C1 and the C2, then your answer is equivalent.